Hello, good day everyone. You are welcome to this channel. Today we are answering question 9 of Pure Mathematics Paper 2, June 2021 session. This question is on complex numbers. And the first part of the question reads, given the complex number z1, which is equal to 4 minus 5i, and z2, which is equal to p plus 4i, where p is a real number, find the value of p for which z1 times z2 bar is purely imaginary, where z2 bar is defined to be the conjugate of z2. We know that if z is a complex number, then z bar is called its conjugate if the product z times z bar is an element of the set of real numbers. That is, if this product gives us a real number, then we call z bar the conjugate of z, and vice versa. We can also call z the conjugate of z bar. So whenever you multiply two complex numbers and the answer is a real number, then one of them must be the conjugate of the other. We also know that if z is the complex number a plus bi, then its conjugate z bar can be given by a minus bi. That is, its conjugate can simply be obtained by changing the sign in the middle. In this question, z1 is given to be 4 minus 5i, and z2 is given to be p plus 4i, where p is a real number. We have also been told that the product z1 times the conjugate of z2 is purely an imaginary number. That is, if you multiply this, we are going to obtain a number which is purely imaginary. But let's first of all look for the product z1 times the conjugate of z2. So this is the same as, we know z1 is 4 minus 5i multiplied by the conjugate of z2. We know z2 is p plus 4i, so its conjugate will be p minus 4i. So this is equal to, if you expand this, we are going to have 4p minus 4 times negative 4i is 16i, minus, we know negative 5i times p is negative 5pi, and the negative 5i times negative 4i is negative 20, since I times I is equal to negative 1. So we know that negative 5i times negative 4i is equal to 20i times I, which is equal to 20 times negative 1, and this is negative 20. So this is equal to 4p minus 20, which forms the real part of this complex number, minus, if you factor out negative I, we're going to have 16 plus 5p multiplied by I. But we are told that the product z1 multiplied by the conjugate of z2 is purely an imaginary number, meaning that the real part of this complex number is 0. That is, 4p minus 20 is equal to 0. And this implies that 4p is equal to 20. And so if you divide both sides by 4, we're going to have p to be equal to 5. We have also been asked to find the magnitude of z1 and the argument of z2 squared. So let's start with the magnitude of z1. Again, z1 is equal to the complex number 4 minus 5i, and so its magnitude is given by the square root of 4 squared plus negative 5 all this squared. And this is equal to the square root of 16 plus 25. So this is equal to the square root of 41. The argument of z2 all this squared is simply 2 times the argument of z2. Recall that the argument of a complex number z raised to the power n is just equal to n times the argument of z. So the argument of z2 raised to the power 2 is simply 2 times the argument of z2. We know that z2 is given to be p plus 4i, but p is equal to 5. So this is equal to 5 plus 4i. So the argument of z2 is given by the tan inverse of 4 divided by 5. And this is equal to 0.675 radians. That is correct to 3 decimal places. This value can be obtained directly from your calculators, and it is exactly equal to 38.66 degrees. That is if you write this to 2 decimal places. Therefore, the argument of z2, all this squared, is equal to 2 times the argument of z2, which is equal to 2 times 0.675 radians. And this is equal to 1.35 radians. In the second part of the equation, we are told that z is equal to x plus iy, where x and y are real numbers, and we have been asked to find the locus of the point z such that the magnitude of z is exactly equal to the magnitude of z minus 2 plus 2i. That is, the magnitude of z is equal to the magnitude of z minus 2 plus 2i, and z is equal to x plus yi. So this implies that the magnitude of x plus yi is equal to the magnitude of x plus yi minus 2 plus 2i. So this is equal to the magnitude of x minus 2 plus y plus 2, all this multiplied by I. So this implies that the square root of x squared plus y squared is equal to the square root of x minus 2, all this squared, plus y plus 2, all this squared. And if we square both sides, we are going to obtain x squared plus y squared, which is equal to x minus 2, all this squared, plus y plus 2, all this squared. So this implies that x squared plus y squared is equal to, if you open the brackets here, we're going to have x squared minus 4x plus 4. And if you open the second bracket, we are going to have y squared plus 4y plus 4. Now, if you subtract x squared plus y squared from both sides, we are going to have, this side we're going to have 0, which is equal to negative 4x plus 4 plus 4y plus 4. So this implies that 0 is equal to negative 4x plus 4y plus 8. And if you divide both sides by negative 4, we are going to have 0, which is equal to x minus y minus 2. So the locus of z is simply the line x minus y minus 2 equal to 0.